Joyce Academy, we'll be discussing a very important topic today. We'll be talking about colligative properties of solutes and solvents. In this kind of context, we'll consider the solvents and the molecules. Colligative property is a property that has to do with the solution and the solvent involved. In simple terms, if you are asked to define colligative property, we say colligative property is a property of a solution that depends on the solute particles and the solvent molecules. This has to be in ratio. So this is the simple definition you can give for colligative properties. We're discussing these four properties on under colligative properties. One is the freezing point depression, another is the boiling point elevation, we have vapor pressure lowering, and osmotic pressure. All these four, there will be an effect of the solvent and the solute in each of these four properties. The freezing point of a particular solute differs because in freezing point we have to consider solute and solvents, trying to compare the two of them. So the difference in freezing point, change in TF, which we calculated, TF will be equal to the change in TF naught minus change in TF. There's a difference between these two. TF naught is the standard freezing point of standard pure solute, and this is the freezing point of that particular solute. So in all, we have to introduce a constant Kf and N. N stands for molality, and Kf stands for the freezing point constant. Freezing point constants can be given before you can calculate the freezing point of a particular solute. So we move to boiling point elevation. Boiling point elevation, this has to do with an increase of the boiling point of a particular solute due to the increase of impurities in that particular solute. So for example, let's consider water. The actual boiling point of water is 100 degrees Celsius. But at times we see that we boil water above 100 degrees Celsius. This is due to some presence of impurities. So impurities have great effect on the boiling point of solutes. So if you want to see the boiling point, the difference in boiling point, for example, let's say TB is the boiling point, and we now want to see the difference if there is an increase or a decrease in boiling point. The actual boiling point of that particular pure solute minus the present boiling point. This will give you the difference in the boiling point if there is an elevation or a decrease, vice versa. If we are to consider vapor pressure of a particular solution can be lowered due to different factors. If you are to calculate the vapor pressure of a particular solution, let's say the solution A, the vapor pressure of the solution A, let's say XA multiplied by P naught A, and for another solution PB, XB, P naught A, where XA is the standard vapor pressure and PA is the vapor pressure of that particular, let's say this is the partial pressure, let's call that partial pressure, and PA is the pressure of that particular constituent or solution we are given. So there will be a difference in each of these pressure. It may be lowered, there may be an increase, this and that. But in this context, we'll be considering the vapor pressure lowering. So if there is a difference between these two vapor pressure, for example, it's a standard solution given to us, and we now consider the same solution at same amount, and there is a decrease, that means there is an effect in the pressure, but it's the same partial pressure. So that's what we mean by vapor pressure lowering.
So what's the difference between PA and PB?
PA is the pressure of constituent A, and PB is the pressure of constituent B given to us.
Okay, so they'll give us different constituents.
Yes.
Is it different solutes or different solutions?
It could be different solution, and it could be of same solution of different partial pressure, of different pressure given in that particular question. They might say vapor pressure of water solution, let's say water, and one of the partial the pressure given to us may be 0.02 atm in atmosphere, okay, and the second distance, same water, that's 0.08 atm atmospheric pressure.
Okay. So what's the why do we have XA and XB?
Now, XA and XB. XA is same in all conditions. Is a partial pressure to be given and to be same. And XB will be the partial pressure given also for that particular context. For example, if you are given the partial pressure of water, you use as an increase or as a reduction.
Okay.
Yeah, you use it for the same thing here. You calculate with this pressure. The only difference is that there's going to be a difference in PA and your PB, which is given 0.02 atm and 0.08. So if the atmospheric pressure, the partial pressure given to you, let's say 2.03, all you have to do is to multiply by each of the pressure given.
So we have PB equal to XB times PA naught. So is it supposed to be PA or PB?
No, actually this is PB. That's it.
Okay. So we have XB times PB.
Yeah.
Okay.
So discussing osmotic pressure. Osmotic pressure. What is osmosis? If you are to consider osmotic pressure, osmosis is the movement of water molecule from a region of higher concentration to a region of lower concentration through a semi-permeable membrane. So if you are considering this osmotic pressure, it is the pressure that is needed to stop the osmosis. So if you are given this, osmotic pressure is solved or calculated using this formula, pi equal to mRT. So the pressure that is needed to stop the osmosis is what we call the osmotic pressure, and M here is the mass, R is the gas constant, and this gas constant is given to be 0.0821 atmosphere. So the T here is the standard temperature, which is 273 degree Kelvin. So if you are given each of these, at times if you have to calculate for osmotic pressure, they will give you this constant, this universal gas constant. In chemistry, it may differ when you go into physics and some parts of physics. They'll give you different constant, but it's given in lots of scenarios. So you just need your mass, your R and your T to calculate. Make sure it's in standard form. So that's all you need for this, and they might give you the osmotic pressure and they'll ask you to calculate for the mass or the temperature. You know this is constant, so they won't ask you to calculate for it. So that's all we need for osmotic pressure. We'll be going deep under each of these properties: freezing point depression, boiling point elevation, vapor pressure, lowering osmotic pressure, because we need a lot of calculation we ought to do or have knowledge of in this context. If you haven't subscribed to Geo Academy, make sure you subscribe to watch more videos on chemistry, physics and other courses that you might need in your undergraduate level. Thank you very much.